Welcome guys. So we need to prove that this statement that we have here is true by mathematical induction here. So the first thing that we get to do, or rather the step number one that we're going to do here is we show that the statement is true for n equals to 1. So what this means here is we're going to equate this here to what we have on the left hand side, this on the right hand side here. So we're going to say n open brackets n plus 1 is equals to n open brackets n plus 1 n plus 2 divided by 3 like this here. So now where there's n, we substitute 1. So we're going to have 1 open brackets 1 plus 1 equal to 1 open brackets 1 plus 1 1 plus 2 divided by 3 here. Now 1 plus 1 I'm going to get a 2 here, and 2 multiplied by 1 we just get a 2 equal to 1 plus 1 we're going to get a 2 multiplied by 1 plus 2 we get a 3 here. Then this is being divided by 3 like this here. So 3 and 3 can cancel. So we're left with 2 being equal to 2 like this here. So now, if this is the case here, then we're going to say this is true for n equals to 1. Now, we go to step number 2, which is the inductive hypothesis. So step 2, we make the inductive hypothesis here. Like this here. So now, under the inductive hypothesis, we just assume that the statement that we have is true for n equals to 1. So here we make an assumption, or just assume that the statement that we have there is true for n equals to k here. So assume that the statement is true for n equals to k. So where there's n in the expression that we have, we just substitute with k there. So meaning that here we're going to have 1 plus 2 so here it's supposed to be 3, then we have a 4 inside there, plus up until now. So we're going to say k, where there's n we substitute the k plus 1 equal to k open brackets k plus 1 k plus 2 divided by 3 here. So it's the only thing that we get to do under the inductive hypothesis, where we just make a substitution. Where there's n, we substitute with k plus with n with k there. Okay. So now the third step here, we need to show that the statement that we have is true for n equals to k plus 1. So what this simply means here is that if we add the new term here, which is the k plus 1 term, the statement should still hold there. So meaning that here we're going to say 1 plus 2 plus 3 plus up until we have the k plus 1 term. Then now we add the k plus 1 term there. So where there's n we substitute with k plus 1. So meaning that here we're going to have k plus 1 open brackets k plus 1 plus 1 is equal to k plus 1 k plus 1 plus 1 k plus 1 plus 2 divided by 3 here. Right. So now when you look at this term here, starting from the first term that you have here up to the k term here, you'll notice to say that these here, they give you the inductive hypothesis that we have here. Meaning that where there are these terms here, we can just substitute with the right hand side that we have this side. So there we have case open brackets k plus 1 k plus 2 then divided by 3 plus here we're going to have k plus 1 plus 2 equal to, open brackets, k plus 1, k plus 2, and k plus 3 here, divided by 3 like this here. So now, our goal here is to show that the left hand side is equal to the right hand side here. So we just simplify what we have on the left hand side. So here, this is the same as over 1 here. So now, we make this a single fraction here by saying the common denominator is going to be 3 here. Then 3 into 3, we get 1. 1 multiplied by what we have here, which is going to have k plus 1, k plus 2, plus 1 into 3, we get 3. 3 multiplied by what we have there, we're going to have 3, k plus 1, k plus 2 like this here. This is being equal to k plus 1, k plus 2, and k plus 3 here, divided by 3 like this here. Then now, here, when you look at what you have on the left hand side, the numerator on the left hand side, you'll notice to say that k plus 1 and k plus 2, k plus 1, k plus 2 here are common on the two terms here. So meaning that when you factor it out there, you're going to have k plus 1, you factor it out, you also factor out k plus 2 here. You notice that here, the only thing that's going to remain there is going to be k. Plus, we check this side, if you factor out k plus 1 and k plus 2 here, the only thing that's going to remain there is a 3 here. So k plus 3 here, divided by 3 equal to k plus 1, k plus 2, and k plus 3 here, divided by 3 like this here. So there we have it. The left hand side is equal to the right hand side. So now, if this is the case here, then this here is true for n equals to k plus 1. So now, if this is true for n equals to k plus 1, then the statement that we have is true under mathematical induction. The statement is true under mathematical induction. Like that there. Alright, thank you.